Hello and welcome. For today's video we are looking at atoms and radiation, and we are looking in particular at half-lives. Now, to understand half-lives we need to look at what the atoms are doing in a particular sample of a radioactive substance. So here I've got a radioactive isotope or a radioactive element, and the way we can measure the radioactivity given off by this is using something called a Geiger counter. And a Geiger counter often counts the count rate per minute for a particular radioactive element or radioactive isotope. Now, to understand this idea of half-lives we need to look at the atomic level. So imagine I took a tiny part of this element, magnified it many times, and was able to see the atoms in that sample. Now here are a bunch of atoms. In actual fact these are the nuclei of those atoms. Usually when we are dealing, in fact always when we are dealing with radioactive decay, we are only looking at the nuclei of the atoms and what's going on with them. So here I've got a sample of 24 of those nuclei, and what we know is that if the substance is radioactive, at some point in time one of these atoms is going to give out its radioactivity, or it's going to give out some radioactivity, and very often that will change which type of atom it is. So I'll represent that by just showing a change in color like that. Now the only problem is we don't know which nucleus is going to decay next. So if you were to try and guess and you had to pick one of these, which one would you pick, and would you be right? And if you had to pick again, would you be right that time? Now I'm guessing most of you haven't or didn't guess the right one, but if you did, it would probably been a coincidence. But the point is that it's very hard to predict. In fact, you can't predict which one is going to decay next, and as you went along, more and more of these would decay. Now, one measurement you can make is the amount of time it takes for the number of nuclei or number of radioactive nuclei to go down by a half, and we can look at this data on a graph. So imagine I did some measurements and I found out that the radioactive count, or the count on the Geiger counter, went down by half every 2 hours. So the count goes down every 2 hours by half the amount. If we started off with 24 nuclei here, as we have here, after 2 hours the count would half. So after 2 hours we've got 2 hours here, and it's half of 24, so it would go down to 12, which is there. Okay, now after a further 2 hours that count would half again. So we go not from 24, but we count from 12 and we half that and we get 6. But we know it takes 2 hours for the count to half, so we go from 2 to 4 and the count is 6. And if we go a further 2 hours later, that 6 would half again and give us a value of 3 after 6 hours. And we can join up these crosses, and what happens is you get a graph showing the radioactive decay of this particular element. Every 2 hours the count goes down by half, and this is a measurement we can actually make to track the radioactivity or the radioactive decay of particular elements. So let's have a look at what we mean by half-life. If we were to try and write it out, half-life is the average time taken for half of the radioactive nuclei of a sample to decay, or you could say the time taken for the count rate to reach half of its start value. Okay, so this is what we mean by half-life. Now let's have a look at this in a slightly different way to the graph we did previously. Now I've got a sample of something, a sample of a radioactive material, and the start count rate as measured on our Geiger counter is 800 counts per minute. And I've not been very good and not labeled the axes, so that's time in mins, and this is the count rate, and that's in counts per minute. Okay, so we start off with a count rate of 800 counts per minute, and the half-life is 20 minutes. Now the first point at time 0 is very easy to plot. It's just at the start rate of 800 counts per minute, so it's 800 there, and the half-life is 20 minutes. So after 20 minutes that count rate would have halved. So we've got 100, 200, 300, 400. That's half of your 800. So after 20 minutes we have a count rate of 400. Now what's the next point? Well, we have to go another 20 minutes. That's up to 40 minutes. And what's happened to the count rate? Well, it's halved. Remember, it's not half of the 800, it's half of the 400. That's the remaining radioactive nuclei that are left. So half of 400 is 200. That's 20 minutes further on, so we go up to 40 minutes and the count is 200, and we carry on like that. So a further 20 minutes later, that's from 40 to 60, we halve our 200, that's down to 100, so that's roughly there, and then we could carry on down to 50, say, and that's around about there. And we can join these points up. That's not done perfectly, but I think you get the idea. We can join these points up, and here we have drawn our radioactive decay curve for this sample that we were talking about in the question. So if you were asked to plot a graph like this or complete a graph like this, and you had the start count and you know the half-life, that's quite straightforward to do. Let's have a look at another example. Here I've already got my half-life curve drawn for me, but it hasn't given me the half-life. So if I had to calculate what the half-life for this sample was, how would I do it? Well, it's a slightly different question, but it's not too difficult. We start off with 100%, so this time I've done it as a percent of the count rate of the start count. So we start off with 100% at the beginning, and I want to know what the half-life is, how long the half-life is. Along the x-axis I've got time in years, so how long does it take for this sample to half its radioactivity? Well, it's a simple case of going from 100% down to 50, because that's cutting it down by half, going across on the graph, and then going down and reading off the graph. So the half-life so far seems to be about 30 years. Now it's a good idea to check for more than one half-life, because remember we said it's the average time taken, so you have to go down by half again. So that's from 50, halfway down is 25, and if I go across and measure down, this graph just by coincidence is almost perfect, but that goes another 30 years. So we've got 30 years here, 30 years here, and let's just go down by half again one more time, and that's gone a little bit further. So the readings I have here are 30 years, 30 years, and this is actually 32 years, and that's what actually does happen with a real half-life curve. You don't get the exact same number every time. That's why we say it's the average time to decay by half. But we got 30 plus 30 plus 32 equals 92, and you would divide that by 3 to get the half-life. So that would be 30.6, I think, around about 30.6 recurring. So we could say the half-life for this seems to be pointing towards 30.6. Maybe we could round it up to 31 years. So that's how you calculate the half-life if you are given a graph. Now the last thing I want to do is yet a different angle. I've got a couple of questions here, and let's see if we can work these out. You might want to pause here and try these for yourself and then look over the answers. If not, I'm going to go through the answers right now. So we have a sample of a radioactive isotope, and it contains 320 million atoms of the isotope. How many will remain after 5 half-lives? So 5 half-lives pass. That just means we have to half this number 5 times. So the start is 320. After 1 half-life, let's just number them, 1, 2, 3, 4, 5. After 1 half-life, we go to 160 million. After 2 half-lives, we half again, so that would be 80 million, then down to 40 million, then down to 20 million, and then down to 10 million. So after 5 half-lives, the count rate would now be 10 million. The second part of the question says the half-life for this material is 30 seconds. How long for the count rate to reach 40 million from the start? So if we start off with 320 million, how long does it take to reach 40 count rate of 40 million? So that we want to get to this figure here, 40 million. How many half-lives have passed? Well, 320 to 160 is 1 half-life, and 160 to 80 is a second half-life, and 80 to 40 is your third half-life, and each half-life is 30 seconds. So we've got 30 seconds, 30 seconds, and 30 seconds. it takes 90 seconds for this substance to reach 40 million. So that's quite a short half-life, and it's giving off lots and lots of radioactivity. And this is a way of working out how much time has passed. So that's various ways of looking at the idea of half-life. You may need to go through the video once or twice perhaps just to make sure you get the individual points, but apart from that, that's me done. Thanks for watching, and I'll see you again soon.